A mature hurricane is basically one of the most efficient thermodynamic engines on Earth.
Yeah, that's a good way to describe it.
Right, because it operates by extracting all this thermal energy from warm ocean waters, and then it converts that heat into kinetic energy, which is just wind.
And then it exhausts whatever's left over straight into the upper atmosphere.
Yeah, so when you are sitting at home tracking a major storm churning across the Atlantic or, the Gulf of Mexico, you are watching a planetary scale heat transfer mechanism happen in real time.
It's massive.
Hmm.
And for the entirety of human history, our relationship with these systems has been, well, entirely defensive.
Right. We analyze the data, we run prediction models, issue evacuation orders.
We build higher seawalls.
Yeah, we build walls.
Hmm.
Because the underlying assumption has always been that a weather system of this magnitude just cannot be negotiated with. You can't alter it.
But there is a shift happening in atmospheric science right now that's starting to challenge that foundational assumption.
Which honestly sounds like pure science fiction.
It really does.
Uh-huh.
But there is recent peer-reviewed research, specifically this really comprehensive stuff coming out in the journal PLOS Water, that is proposing a theoretical framework for actually subtly steering massive storms.
Steering a hurricane.
Yeah, we are looking at a proposition that pairs advanced artificial intelligence and high-resolution atmospheric modeling with targeted weather modification.
To disrupt the storms days before they ever make landfall.
Oh, right.
Welcome to Meteorology Matters, the podcast that dives deep into the science, chaos, and stories behind the weather that shapes our world. This show was created by meteorologist Rob Jones.
So today, we are really unpacking the gap between these theoretical AI weather models and the physical reality of atmospheric science.
Because it's a huge gap. We are going to examine the microphysics of cloud seeding, the historical precedents of, past attempts to manipulate massive storms.
Yeah, we definitely have to get into the intense ethical dilemmas that pop up when you try to alter natural systems.
Yeah, the legal side of that is wild. Plus, we will explore how meteorologists working today are constantly forced to untangle this real, evidence-based science from the flood of weather control conspiracy theories that inevitably show up online after every major heat wave, flood, or hurricane.
To really understand the motivation driving this new wave of research, we kind of have to look at the current vulnerability of our infrastructure.
Because things are failing.
They are. We are dealing with a climate reality where the frequency and the intensity of extreme weather events are just placing unprecedented stress on you, on your community, on coastal areas, and inland power grids.
Yeah, and the research we are looking at today, which was co-authored by Upmanu Lal over at Arizona State University, it opens with a very stark assessment of our current defenses.
Because the dams, the levees, the seawalls, even financial safety nets like your insurance policies, they are increasingly insufficient to handle these hazards.
We have spent decades basically engineering physical barriers based on historical flood data, right?
Yeah.
And historical wind speeds.
But that baseline is shifting. The water is getting too high. The storms are getting too strong. So the traditional strategy of just building a taller concrete wall, it's yielding diminishing returns.
Right. So the authors of this research are suggesting a fundamental pivot. Instead of a defensive posture, they want to move to active, calculated intervention.
Which is a huge paradigm shift. Their proposed solution involves leveraging existing delivery mechanisms like the technology we currently use in cloud seeding operations.
But supercharging it.
Yeah, supercharging it by integrating it with a new generation of high-tech, atmospheric data collection, real-time observations, and very sophisticated AI modeling.
So the goal isn't to build a larger wall. The goal is to use AI to calculate the exact precise time and physical location to introduce a minor atmospheric disruption.
A nudge.
A nudge, yeah. The theory is that this tiny disruption could cascade through the whole weather system and fundamentally alter its trajectory or its intensity before it hits a city.
And the researchers actually provided 3 specific historical hypotheticals to illustrate the scale of this. And the claims are, frankly, staggering.
Yeah, let's go through those because they applied this theoretical framework to past events to model what an intervention might have looked like.
The first one is Superstorm Sandy from 2012.
Oh, wow. Okay.
Yeah. They suggest that with a carefully timed, localized operation applied days in advance, they could have shifted the track of Sandy by about 300 miles.
Wait, 300 miles?
Yeah, skewing the system so it would have completely bypassed New York City.
I mean, a 300-mile displacement for a system the size of Sandy is just a monumental alteration of atmospheric steering currents.
It really is. Sandy was uniquely devastating because of its massive wind field. It spanned nearly 1,000 miles.
And it had that highly unusual left hook into the New Jersey coastline.
Driven by a blocking high-pressure system in the North Atlantic.
Right. So to alter that interaction so drastically, it implies a level of control over synoptic scale features that goes way beyond anything we can currently do.
Way beyond. And the hypotheticals don't stop at tropical cyclones. The second scenario focuses on the Texas freeze of February 2021.
That was devastating.
It was. And the study suggests that an intervention could have raised the low temperatures of that polar air mass by roughly 18 degrees Fahrenheit.
18 degrees. In meteorological terms, an 18-degree modification to a continental polar air mass, I mean, that is the difference between widespread catastrophic infrastructure failure across the entire Texas power grid and just a manageable standard winter day.
Yeah, it changes the entire event. And finally, they applied this AI modeling to a 2022 California atmospheric river.
Okay, and what did they say for that one?
They proposed they could have reduced the precipitation carried by the system by 5%.
Just 5%.
Yeah, which sounds small, but they calculate that would have been enough to mitigate the most severe flooding impacts.
So the authors have to know how audacious these claims sound to the rest of the meteorological community.
Oh, they are fully aware. So to try and contextualize this theoretical framework, they're relying on a specific analogy. They call it weather jujitsu.
Weather jujitsu. Okay.
Yeah, Manu Lal explains that the fundamental principle of jujitsu is achieving maximum physical efficiency with minimal applied effort.
Right, so a smaller defender doesn't try to match the brute strength of a massive attacker.
They use leverage, precise timing, and the attacker's own momentum against them.
So in this framework, human intervention is the smaller defender, and the massive incoming hurricane or atmospheric river is the attacker.
That's the idea. The entire theory hinges on the inherent chaos of atmospheric dynamics. You know, the atmosphere is a nonlinear dynamical system.
Meaning it is highly sensitive to initial conditions.
The classic butterfly effect.
Yeah.
So they hypothesized that if AI can just ingest enough high-resolution data to find the exact atmospheric pressure point, a really localized intervention applied days before the storm's peak could multiply over time.
It leverages the system's own momentum to create a cascading effect that alters the track. I have to challenge this premise, though, by taking their own analogy a step further. Because in martial arts, the defender has to maintain a physical connection to the attacker to apply that leverage, right?
Right.
In meteorology, trying to apply a subtle nudge days in advance to alter a hurricane track by 300 miles, it sounds less like leverage and more like trying to reroute a speeding freight train by placing a single coin on the tracks 3 miles down the line.
It's a great analogy.
Like, can a localized disruption actually cascade into a synoptic scale shift? Or does the sheer volume and energy of the atmosphere just absorb that tiny disruption and keep going on its original path?
And that is the central physical question dividing the theoretical modeling community and observational meteorologists right now.
Yeah.
To evaluate whether this cascading effect is actually physically viable, we have to look closely at the delivery mechanism they suggest for initiating this nudge.
Which brings us to cloud seeding.
It does, and it is critical to define what cloud seeding actually entails today in reality as opposed to how it's portrayed in popular culture.
Right, because when you hear the term weather modification, imaginations run straight to science fiction. You know, machines generating storms out of thin air.
But the actual science of cloud seeding is highly specific. It's narrow in scope, and we've been doing it for decades.
So what is it fundamentally?
It's basically a process of altering the microphysics of an existing cloud by introducing tiny particles into it. The most common agent used is a chemical compound called silver iodide.
Silver iodide? Why that specific chemical?
Because its crystalline structure is remarkably similar to the structure of natural ice.
Oh, I see. And that structure is the key to the whole thing.
Yeah, because inside a developing cloud, water droplets often stay in a liquid state, even when the temperature drops way below freezing.
We call that supercooled liquid water.
Right. So in order for that supercooled water to actually transition into a solid state, to freeze into an ice crystal, grow into a snowflake, and fall out of the cloud, it needs a nucleus.
It needs a tiny particle to grab onto, like dust or sea salt, or in this case, silver iodide.
Yeah, it needs a foundation. So meteorologists inject silver iodide flares into the updraft of a cloud. They do this either using aircraft flying through the storm or ground-based generators on mountainsides.
So they are introducing artificial ice nuclei into the system.
And then those supercooled water droplets rapidly freeze onto the silver iodide particles. As they freeze, they grow heavier, and eventually they overcome the updraft velocity and fall to the surface as rain or snow.
But the reality of what this achieves is pretty limited, right? I mean, NOAA, which is NOAA, the National Oceanic and Atmospheric Administration, and the Government Accountability Office, they say the realistic uses for this are very modest.
Very modest. It's mostly used to just marginally enhance precipitation over specific drought-stricken watersheds, or over mountain ranges to build up the winter snowpack.
And agricultural regions use it too, right? For hail.
Yeah, to suppress large hail. Basically, they seed a thunderstorm to create an abundance of small ice particles. Those particles compete for the available moisture, which prevents the formation of massive, crop-destroying hailstones.
But the crucial distinction here, for you listening, is that cloud seeding operations are merely attempting to squeeze a fractional amount of additional moisture out of a cloud that is already highly conducive to producing precipitation.
It requires pre-existing moisture, pre-existing lift, and pre-existing instability. You cannot seed a clear blue sky and conjure a rainstorm.
No, the current legal and operational landscape in the U.S. reflects this highly constrained utility. Cloud seeding programs are actively managed in 9 Western states.
Mostly funded by water conservation districts and utility companies looking to secure water resources.
But despite its modest impacts, it is highly controversial. 10 different states have recently considered or enacted legislation to ban the practice entirely.
Yeah, Florida, for instance, passed legislation that outlawed the practice within the state starting in 2025.
So this legislative and scientific reality highlights a massive logical gap in the weather jiu-jitsu proposal.
It really does.
If the current operational limit of cloud seeding is essentially wringing out a few extra inches of snow over the Sierra Nevada mountains under ideal winter conditions, jumping from that to steering a Category 4 hurricane feels like skipping several chapters in a physics textbook.
The leap from microphysical cloud alteration to synoptic scale system steering is immense.
Have the study's authors address that?
They have. They acknowledge the magnitude of this technological leap. Manu Lal has noted that while their AI modeling demonstrates the theoretical viability of a targeted disruption, they are still trying to figure out the optimal physical mechanism to actually deliver that nudge in the real world.
So they don't even know how they would do it yet.
Not definitively. He suggested that a massive, unprecedentedly dense cloud seeding effort executed at the exact right time and place is a potential delivery method.
But that would require logistical coordination and scale way beyond any existing program.
And this is exactly where the broader meteorological and atmospheric science community steps in with foundational reservations about the physics here.
Yeah, I saw Katja Friedrich, an atmospheric researcher at the University of Colorado. She stated unequivocally that there is zero scientific evidence supporting the idea that existing cloud seeding technologies can be scaled up to modify large-scale, severe weather systems.
Her skepticism is rooted in a concept we call large dynamic forcing.
Let's unpack large dynamic forcing because this is the fundamental barrier to the whole jiu-jitsu analogy.
It is the engine that drives severe weather systems, from sprawling thunderstorm complexes all the way up to mature hurricanes. And it explains why steering these systems is so phenomenally difficult.
Right, because a hurricane is not merely a localized cluster of thunderstorms that you can just manipulate by sprinkling chemical agents into an updraft. It is a massive heat engine operating on a planetary scale.
It feeds continuously on the thermal energy stored in the upper layers of the ocean.
Right. To sustain a mature tropical cyclone, sea surface temperatures typically need to be at or above 80 degrees Fahrenheit.
And as that warm ocean water evaporates, the moisture rises into the atmosphere, it cools, and it condenses to form those towering cumulonimbus clouds in the eye wall and the rain bands.
And during that condensation process, the water vapor releases latent heat into the surrounding atmosphere.
That release of latent heat is the critical driver. It warms the air aloft, causing it to expand and diverge outward from the center of the storm.
And that divergence aloft is what lowers the atmospheric pressure at the surface.
Which then draws in more warm, moist air from the ocean, which spirals inward, rises, condenses, and releases even more latent heat.
It's a massive, self-sustaining feedback loop. The sheer volume of energy being converted and released is staggering.
Furthermore, the environmental forces dictating the path of that engine are are equally massive.
Mm.
A hurricane is steered by the ambient planetary scale wind currents embedded in the troposphere.
Yeah, it's guided by the clockwise flow around semi-permanent high-pressure systems like the Bermuda High in the Atlantic.
Or it's pulled and deflected by deep atmosphere troughs moving across the mid-latitudes.
And consider the scale of major climate patterns, right? Like El Niño, pronounced El Niño, or La Niña, pronounced La Niña.
An El Niño pattern fundamentally alters global atmospheric circulation.
It shifts the Walker circulation across the equatorial Pacific, which then cascades into changes in the upper-level wind shear across the Atlantic basin.
Which can completely suppress hurricane development over an entire ocean.
Right, so when you are dealing with thermodynamic forces driven by ocean basin temperatures and steering currents dictated by global phenomena like El Niño, injecting silver iodide into a small section of a rain band is an infinitesimally small intervention.
Returning to the jujitsu analogy, a tiny localized nudge is highly likely to just be absorbed and instantly dispersed by the overwhelming energy of the storm's large dynamic forcing.
It's akin to attempting to change the course of a raging river by dropping a single pebble into a Class 5 rapid. The internal energy of the system simply overwhelms the disruption.
And the interesting thing is, we actually possess historical data that illustrates this exact discrepancy between theoretical modification and physical reality.
Right. Carl Lamb, an associate research scientist at Columbia University, pointed out that the meteorological community attempted similar interventions decades ago.
The United States government actively tried to use cloud seeding to weaken hurricanes.
And the effort failed to produce any reliable, replicable results.
She is referencing Project STORMFURY.
STORMFURY, yeah.
Mhm.
That was a highly ambitious federal research initiative, right? It ran from the early 1960s through the early 1980s.
And the theory behind STORMFURY was actually grounded in that understanding of latent heat we just discussed.
So what was their hypothesis?
They thought that by heavily seeding the first rain band situated just outside the hurricane's intense inner eye wall, they could induce the supercooled water in that outer band to freeze.
Okay, and that freezing process would release a massive amount of latent heat in the outer band.
Right, which would then stimulate the growth of a new, wider eye wall that would eventually choke off and replace the original tighter eye wall.
Because the physical rationale was based on the conservation of angular momentum. The idea was that if you force the storm to develop a wider eye, the maximum wind speeds would decrease.
Like an ice skater throwing their arms outward to slow down a rapid spin.
Right, so if you expand the radius of maximum winds, you theoretically drop the storm's category and reduce the catastrophic wind damage at landfall.
And the physics appeared entirely sound on a chalkboard.
So they actually tested it.
Oh yeah, the project involved flying heavily modified military aircraft directly into monstrous hurricanes churning in the Gulf of Mexico and the Atlantic.
To deploy thousands of silver iodide flares.
Directly into the storms. And in a few early instances, most notably Hurricane Debby in 1969, the wind speeds did actually decrease following the seeding runs.
Which initially fueled massive optimism.
It did. But as the project continued and our atmospheric observational technology improved throughout the 1970s, the results became entirely inconclusive.
And decades later, meteorologists identified exactly why the hypothesis failed in practice.
There were two major physical flaws. First, comprehensive data collected from aircraft penetrating the storms revealed that hurricanes actually contain very little supercooled liquid water to begin with.
Because the updrafts in a hurricane are generally weaker than the violent updrafts in, say, a continental severe thunderstorm, right? So the moisture has time to freeze naturally.
Exactly. The storms are mostly composed of ice crystals already, meaning the silver iodide had very little supercooled water left to act upon.
And the second flaw?
More importantly, meteorologists discovered a natural phenomenon known as eye wall replacement cycles.
Which are entirely natural, internally driven processes that occur frequently in mature, intense hurricanes.
The storm will spontaneously form a secondary outer eye wall that slowly contracts. That cuts off the moisture inflow to the inner eye wall, causing the inner eye to collapse.
And during this natural cycle, the storm's wind field expands and its maximum wind speeds temporarily decrease.
Which is exactly what the STORMFURY scientists thought they were artificially triggering with the silver iodide.
Oh, wow. So they were just observing a natural process and taking credit for it.
Pretty much. This historical reality brings up the absolute core issue in weather modification research, which is natural atmospheric variability.
Right. If you fly an aircraft into a hurricane, deploy a payload of silver iodide, and observe the maximum sustained winds drop by 15% over the next 12 hours, how do you definitively prove your seeding operation caused that drop?
You really can't. What if the storm simply ingested a localized pocket of dry Saharan air?
Or what if it experienced a subtle, undetected increase in vertical wind shear?
Or what if it was just undergoing a natural eye-wall replacement cycle that would have happened regardless of human presence?
Carl Lamb emphasized this exact complication. The atmosphere is an incredibly noisy, chaotic environment.
It is profoundly difficult to separate the signal of a human intervention from the overwhelming noise of the atmosphere's natural variability.
It's remarkably similar to taking a new experimental vitamin to cure a cold. If you take the vitamin on Tuesday and you wake up feeling better on Friday, it's incredibly tempting to credit the vitamin.
Sure.
But it's almost impossible to separate the intervention from what your immune system, or in this case, the thermodynamic engine of the atmosphere, was going to do anyway.
In meteorology, you cannot run a clean control group on a live hurricane.
No.
Yeah.
You can't rewind the atmosphere, remove the silver iodide, and observe what the storm would have done if left completely alone.
That historical context is so vital, but let's play devil's advocate for a moment.
Okay.
Let's operate under the assumption that the authors of the PLOS water study are correct about the future of technology.
Okay, let's assume AI, quantum computing, and data collection advance to a point where they can perfectly model the fluid dynamics of the atmosphere.
They find the exact jujitsu pressure point, deploy the perfect intervention, and guarantee a 300-mile shift in a hurricane's track.
So humanity successfully overcomes the physics of large dynamic forcing.
Right. But if we do that, we instantly crash into a completely different, arguably more insurmountable barrier.
The ethical and legal hurricane?
Yes. Let's re-examine the study's primary hypothetical, Superstorm Sandy.
Okay, so the theoretical claim is that with a precise AI-calculated nudge, they could have shifted Sandy's track 300 miles, successfully steering the storm surge away from a direct hit on New York City.
And given the population density, the subway system, the vulnerable infrastructure, New York is uniquely susceptible to catastrophic flooding.
So shifting that storm successfully protects millions of people in the New York metropolitan area and saves billions in infrastructure.
It does. But weather modification on a synoptic scale is a zero-sum game. A massive, potent weather system containing millions of tons of water and staggering kinetic energy does not just evaporate because you altered its steering currents.
Right, it has to go somewhere.
If you shift a system like Sandy 300 miles away from New York City, it is going to maintain its structure and slam into the coastline of New England instead.
You are no longer engaging in passive forecasting. You are actively, deliberately choosing which coastline absorbs the impact.
You are sitting in a room deciding which coastal towns get wiped off the map, whose homes are submerged in a 12-foot storm surge, and whose lives are placed in severe jeopardy.
This is the ultimate ethical dilemma. You are taking the unpredictable, indifferent chaos of a natural disaster and applying human agency to it.
Robert Rauber, a director emeritus in the Department of Climate, Meteorology, and Atmospheric Sciences at the University of Illinois, captured the insurmountable scale of this problem.
What did he say?
He argues that major storms involve incredibly complex atmospheric flows over vast oceanic regions, evolving in nonlinear ways. He points out that even if physicists mastered the mechanics to reliably move these storms, the political, international, and legal fallout would be so immense that the technology would likely never be deployed.
The legal ramifications alone are enough to paralyze any government agency. Imagine a scenario where a federal agency, let's say NOAA or the EPA, were granted the operational authority to manage this weather steering program.
Okay, picture this. A Category 4 hurricane is bearing down on Miami.
The agency runs the AI models, deploys the intervention, and successfully nudges the storm away from Florida.
But the new track directs the storm directly into Savannah, Georgia.
The ensuing litigation would be unprecedented in human history. The state of Georgia would have grounds to sue the federal government for intentionally directing a catastrophic, deadly disaster onto its citizens.
Insurance companies holding policies in Georgia would face insolvency and would inevitably sue the operating agencies for massive liability.
The concept of sovereign immunity would be tested in ways the legal system has never encountered.
And that scenario only considers domestic borders. The geopolitical implications are significantly more volatile.
What happens if a rapidly intensifying hurricane is moving through the central Gulf of Mexico, and the United States decides to nudge the system westward to protect the vulnerable refineries along the Texas coastline?
Well, if that nudge inadvertently causes the steering currents to collapse, stalling the storm and dumping 40 inches of rain over vulnerable regions in Mexico or Cuba, you have initiated an international incident.
You are instantly dealing with accusations of weaponizing the weather, even if the intent was purely defensive.
There are already international treaties in place, like the Environmental Modification Convention, designed specifically to prohibit the hostile use of environmental modification techniques.
The geopolitical instability caused by one nation unilaterally deciding where a hurricane makes landfall is staggering.
It is. It really is worth noting the perspective of the researchers on this issue, though. The study authors, including Upmanu Lal, explicitly state that their current focus is entirely on developing the mathematical, scientific, and engineering capacity to see if the theory holds up. They acknowledge the ethical frameworks, legal liabilities, and control issues are massive hurdles, but they maintain that their role as scientists is to establish the physical possibilities first, leaving the ethical and policy questions for lawmakers and ethicists to resolve in the future.
I have to strongly challenge that dismissal, though, because in the realm of applied meteorology, you really cannot sever the scientific research from its real-world impact.
Yeah, the two are inherently linked.
The stated justification for this entire study is the fact that traditional defensive infrastructure is failing to protect highly populated areas. The goal of the technology is to save major cities.
Right.
But that goal inherently and unavoidably requires redirecting that destruction toward less populated or simply different areas. The ethical dilemma isn't an unforeseen side effect, it is the core mechanic of the proposed solution.
You can't just invent a technology designed to divert a natural disaster onto a new target and simply say that the legal department will figure out the ethics later. The capability itself forces the ethical crisis.
And this intense anxiety surrounding the idea of humans playing God with the atmosphere, it isn't merely a theoretical debate reserved for a hypothetical future where AI reaches maturity.
No, it is a present-day crisis, deeply affecting the meteorological community.
The very fact that credible scientists are publishing peer-reviewed literature about theoretical frameworks for steering hurricanes feeds directly into one of the most exhausting challenges modern broadcast and operational meteorologists face today:
The rampant spread of weather modification misinformation.
We witness this phenomenon every single time a major weather disaster strikes anywhere on the globe. Real meteorological research, theoretical modeling, and routine cloud seeding operations are routinely stripped of their nuance, taken completely out of context, and weaponized into viral online conspiracy theories that spread faster than the actual weather warnings.
We can observe this dynamic clearly in two recent, highly publicized and tragic events. Consider the catastrophic Texas floods of 2025.
That was a devastating synoptic setup.
It was. An anomalous amount of atmospheric moisture was transported over the region, resulting in massive rainfall rates over a very short period.
The ensuing flash flooding led to rapid, widespread inundation, tragically resulting in the deaths of dozens of people, including many children who were caught in the rapidly rising waters.
The communal grief, shock, and desperate search for answers following an event of that magnitude are profound.
But almost immediately after the waters began to rise, viral claims exploded across various social media platforms, alleging that a nearby routine cloud seeding operation conducted by a local water district actually caused the catastrophic rainfall.
And meteorologists and emergency management officials were forced to divert critical time and resources during an ongoing recovery effort just to debunk these claims.
Experts across the field had to repeatedly confirm that there was zero empirical evidence linking any local seeding operations to the synoptic scale flooding.
They had to publicly reiterate the scientific reality of large dynamic forcing that we discussed earlier.
Because a routine glaciogenic cloud seeding operation, designed to marginally enhance rainfall from an existing system, physically lacks the capacity to generate the massive atmospheric moisture transport, the intense vertical lift, and the sheer thermodynamic energy required to create a stationary, catastrophic flood of that magnitude.
A virtually identical situation unfolded on the international stage, too.
Right. In April 2024, the United Arab Emirates experienced a historic, record-shattering rainfall event.
The system dumped over a year's worth of rain on the region in a matter of hours, causing massive, unprecedented flooding in Dubai.
The imagery of modern multi-lane highways completely submerged underwater-dominated global news cycles.
And instantly, identical conspiracy theories saturated social media, explicitly blaming the flooding on cloud seeding.
Because the UAE does maintain a well-publicized active cloud seeding program to combat their severe regional water scarcity.
Since the public was generally aware of this program, theorists immediately correlated the existence of the program with the extreme weather event.
However, atmospheric scientists and regional officials unequivocally confirmed that no seeding aircraft were deployed and no seeding missions occurred prior to or during the severe weather outbreak.
The actual meteorological cause of the Dubai flooding was extensively documented and forecasted days in advance.
It was driven by a slow-moving, deep, upper-level cutoff low-pressure system interacting with a highly anomalous surge of tropical moisture moving across the Arabian Peninsula.
It was a completely natural, synoptically driven weather system, exacerbated by the background reality of a warming climate.
Which fundamentally allows the atmosphere to hold and transport higher volumes of water vapor.
Yet the narrative that a government aircraft had manually flooded the city spread exponentially faster than the actual thermodynamic explanation.
Observing this repeated pattern really forces us to examine the psychological drivers behind the misinformation. Why do these specific conspiracy theories find such fertile ground?
Why is the listener constantly seeing these specific claims algorithmically promoted on their timelines after every severe weather event?
It fundamentally comes down to the human struggle between control and chaos. It is psychologically terrifying for the human brain to truly internalize that the atmosphere is a wildly chaotic fluid dynamics problem.
It is deeply unsettling to accept that a Category 5 hurricane can wipe out a vibrant coastal city simply due to a random, unlucky alignment of oceanic heat content, lack of wind shear, and upper-level steering currents.
It is terrifying to accept that the baseline of these natural extremes is shifting in unpredictable ways.
For many people, it is actually deeply psychologically comforting to believe that a secretive organization or a shadow government agency is manually controlling the weather.
Because if a human being is controlling the storm, it means the universe isn't random.
Means there's a specific, tangible villain to blame, rather than facing the cold, indifferent, and uncontrollable physics of nature.
The human brain relies heavily on pattern recognition and the assignment of agency. When confronted with an incomprehensible natural disaster, assigning deliberate blame to a human actor, even a malevolent one, can paradoxically feel safer and more manageable than accepting our absolute vulnerability to planetary-scale natural forces.
But recognizing that psychological vulnerability brings up an incredibly difficult question for the scientific community.
Right. When peer-reviewed literature, like the PLOS water paper we are analyzing today, is published, publicly discussing the theoretical possibility of steering hurricanes using AI and cloud seeding technologies, doesn't that inherently, albeit accidentally, provide ammunition to the very conspiracy theorists who are already claiming that the government is actively doing it?
It creates an incredibly precarious communication tightrope for the entire scientific community.
On one side of the balance, the fundamental integrity of the scientific method requires open, unhindered inquiry. Researchers must have the freedom to explore theoretical boundaries, run complex simulations on supercomputers, and ask profound what-if questions without being constrained by the fear of how the general public or bad actors might misinterpret their data.
Stifling peer-reviewed research because of potential social media misinformation fundamentally harms scientific progress.
But on the other side of the balance, scientists, universities, and institutions must practice radical clarity in their public communication.
They must rigorously and repeatedly distinguish between a theoretical computer model simulating an event in a laboratory and the physical operational capabilities that actually exist in the real world.
We have to continually emphasize that running a simulation on a supercomputer that demonstrates a 300-mile shift in a hurricane's track is entirely disconnected from actually possessing the physical delivery mechanisms, the thermodynamic power, or the legal authorization to fly a fleet of aircraft into a Category 5 storm and physically alter its trajectory.
Maintaining that precise distinction is critical. Operational meteorologists are frequently caught in the crossfire.
They are tasked with explaining the fascinating theoretical advancements in atmosphere science and artificial intelligence, while simultaneously fighting a rearguard action to debunk the weaponized misinformation that willfully conflates that theoretical science with operational reality.
It is a relentless battle for empirical truth within a very noisy, chaotic information ecosystem.
And it leaves the meteorological community in a fascinating, deeply unsettling position regarding the future of weather forecasting, mitigation, and theoretical modification.
It really does.
So, we want to leave you with a final thought to mull over as you watch the weather evolve this week. We are currently living through an era of exponential technological growth. The artificial intelligence models analyzing our atmospheric data are becoming sharper, faster, and more precise with every passing hurricane season.
If the theoretical physics proposed by researchers today continue to evolve, we might very well reach a point in the near future where a supercomputer can output the exact mathematical solution required to perfectly nudge a massive storm.
The AI might provide the exact atmospheric coordinates, the exact temporal window, and the exact physical mechanism to shift a landfalling hurricane, theoretically possessing the blueprint to save thousands of lives in a major coastal city.
But because of the insurmountable legal liabilities, the staggering geopolitical nightmare of actively choosing which community absorbs the redirected impact.
And the sheer physical limitations of actually deploying that intervention against the massive dynamic forcing of the atmosphere.
Humanity might find itself utterly paralyzed to act on that knowledge.
Will possessing the exact mathematical blueprint to save a city, while lacking the physical capability or the ethical framework to execute it, become the ultimate meteorological tragedy of the 21st century?
It's something we'll all have to face eventually.
If you want to keep exploring the fascinating, chaotic world of atmospheric science, extreme weather, and the forecasting technology that keeps us safe, make sure to follow Rob Jones on Instagram, TikTok, YouTube, and Facebook for daily weather updates and deeper insights. Also, please take a second to like, follow, comment, and rate the podcast on whatever platform you are using right now. It really helps the algorithm and allows us to keep bringing you these in-depth conversations.
And it really does help.
You've been listening to Meteorology Matters, created by meteorologist Rob Jones. Thanks for listening, and remember, meteorology always matters.